Okay, so I guess we will start. Welcome everyone. Today we are having Surbhi's second lecture on quantum chaos in ATSCF. Over to you, Surbhi.
Thanks, Rohit. As you saw that last time, in the last lecture, we covered the introduction, and we were kind of midway through the derivation of out-of-time ordered correlator in a thermal 2D CFT. A brief recap of the relevant parts. So we were computing the out-of-time order correlator. One second. Yeah, we were computing the out-of-time order correlator at the following locations on the thermal 2D CFT. These are the operator locations. I've just written the x component, so just the x coordinate. And similarly, there will be like the x bar coordinate, which will just have like minuses here. No, also signs like that. So that's the x bar. And we saw that the out-of-time order correlator, the normalized out-of-time order correlator, can be written as an expansion in Virasoro blocks. And then we took the following limit, t goes to infinity. In that limit, the cross ratios go to 0. This is called the OP limit in the literature. I can refer the paper on Slack. So the Virasoro block expansion of the 4-point function in this limit is dominated by the identity block. So the normalized out-of-time order correlator is just the following function. It's just given by the identity block. Now, okay. Now let's look at the form of the identity block. So the identity block V0 eta in the heavy light limit. So what I mean by this limit is that for a large CCFT, large central charge CFT, the conformal dimension of one of the operators is kept fixed and small. And for the other operator, it is taken to be large, which means that HV is much larger than 1, but it is still much smaller than the central charge. So in this limit, V0 eta is just the following function. And as you can see that this function has a branch cut from 1 to infinity. So let me draw that. In the complex eta plane, complex plane of the conformal cross ratio. Right. So
Surbhi, Avik has a question, so if you want to take
yes.
it now.
Yeah.
Yes, so here this HV over C, is it of the order of HW over C, or is it smaller?
HV over C will be larger than
HW over C.
Yeah. Because that's HW is the lighter operator, right?
Okay, yeah. HV is still much smaller than C. So.
Yeah. So I think what that means is that since it is much larger than 1, HW over C is kind of the order of 1 or even smaller. Is smaller than 1 actually.
Oh, yeah.
Yeah, so this function has a branch cut because of the factor here to the power 1 minus HW by C. So what that means is that, right, so let's just take this and try to understand what that means. So recall that this was the cross ratio that we had already seen in the last lecture. And this cross ratio has the singularity when t becomes equal to sigma. So what happens is that this cross ratio, it actually crosses this branch cut at t equals sigma. So basically this function is multi-valued. 1 minus eta is also a solution. And another solution to this function is 1 minus eta e to the power minus 2 pi I. Now, which solution do you choose? Which is the physical solution? That's the question. So what we see is that for the out of time order correlator, when we have, so by out of time ordering, we have this epsilon 1 less than epsilon 3 less than epsilon 2 less than epsilon 4. When we substitute this out of time ordering in the cross ratio and we simulate in Mathematica, as time increases, the out of time order correlated crosses this branch cut. Whereas if we did not have this out of time ordering and we were looking at just the time ordered correlator, the cross ratio would never cross the branch cut when we increase the time. So basically, for out of time ordering, we need to select this solution. We need to go to the second sheet. That is, we need to cross the branch cut to get the correct out of time ordered correlator. Right.
Hi, Surbhi. I had a
Yeah.
question. So can you just go back? Why do you
Yes.
have a, I mean, is it very obvious to see that this is a quadratic branch cut? I mean, yeah, why is it only quadratic?
What do you mean? Like, what
I
made
mean,
you?
you have only 2 sheets, no?
Yes. Right. So it need not be only it need not have only 2 sheets. It can have more sheets, but it's the, I mean, so for the exponential decay in what we are interested in, it's sufficient to look at just these 2 sheets, because the other sheets will give subleading corrections to the exponential decay.
Okay. Okay.
I mean, there could be, so you're right that we could also have 1 minus eta to the power e to the power 2 pi k. But
Right.
then those sheets give subleading corrections.
Okay. Thanks.
Sorry, is it not like, I mean, I'm just going from t equal to 0 to t equal to infinity, hence I'm just crossing. Why should I cross multiple times?
I mean, mathematically, it's possible actually to cross multiple times. But
yeah, I understand, but physically, it's like you are going from t equal to 0 to t equal to infinity. Right?
Yeah, that's true.
That's
Yes.
just you are crossing it once.
Yes.
I mean, even if you're crossing it once, that does not mean that function is not
Yeah,
multivaluable.
there are, but I think those are, I mean, yeah. It's
That's
like
fine. That's what she answered earlier. I agree. Yeah.
Okay. So then, right. So basically for, I think I had that. Yeah. Right. So for sigma greater than 0, so we're just constraining to have the x coordinate of in the out of time order in the operator locations in the out of time order correlator, the spatial coordinate to be positive. In that case, the cross ratio eta crosses the branch cut. So it crosses the branch cut, whereas eta bar does not. So 1 minus eta goes to e to the power minus 2 pi I, 1 minus eta. And when we substitute this in the OTOC, which was so we get V0 eta to be 1 over 1 minus 24 pi I HW by C eta. And this doesn't cross the branch cut, so we get that to be just 1 in the, sorry, this is just 1 in the late time limit. And then substituting the cross ratio. So in the last lecture, we had derived the cross ratio as an exponential, and substituting that here, we get the OTOC to be the following.
Before you go to the next slide, Shubham has a question.
No, it's fine. Like I think I'll ask.
Okay.
Slack.
Okay, then we have a question in this chat that does not branch cut mean that we decide we cannot cross them, so we try to avoid it and draw contour accordingly. So crossing here means choosing the branch or something else. That's what
choosing the sheet. So basically, to get the out of time order correlator is the correlator becomes out of time ordered only on the second sheet. So I'm choosing to be on the second sheet to get the correct time ordering.
So can I briefly comment to Rohit's question?
Yes, go ahead.
Sure.
Yeah, so here actually, we do not actually have a choice. Once we have chosen the hierarchy of epsilons, if we follow the trajectory of this theta in the plane of this cross ratio, then we see that once we have this out of time ordered kind of hierarchy, then the turning point actually crosses the line between 1 to infinity. So once we have made a choice for epsilon, now we don't have a choice like you will cross it. Where it so happens that for the POC kind of ordering, it does not cross the branch cut. So for the OTOC, it crosses the branch cut, takes you to the other sheet, and hence you get the different behavior that she wants.
Okay, thanks, Avi. Any more questions?
Could you roughly show how this eta changes with time, like us?
Right. So yeah, as I drew here, basically the eta increases with time at t equals sigma. You can see the singularity in the cross ratio. At that time, it crosses the branch cut, and it will keep on increasing. And at time equals infinity, it goes like it's still on the second sheet, and eta is very small. So that's the evolution in time of this cross ratio. You can just feed this in math. I mean, it's an exercise to do. You can just feed this in Mathematica, put this ordering of the epsilons, and you can see this happening. Okay. Right. So then the out of time order correlator becomes the following after we substitute the cross ratio here. Yeah, so we get for the out of time order correlator just 1 divided by 1 plus 24 by I. Here T star is the scrambling time. So what I can do is I can even for so this is the out of time order correlator in the heavy light limit. I can take a further light limit. What that means is I will even take HV to be small. So in that limit, what I get the OTOC to be the following. So here I just wrote it in this form to show you what the scrambling time was, but now I'm just writing it with the central charge because I want to use it in that way later. So this is the form of the out of time order correlator, which some of you might have seen. This is right now we derived it from a CFT computation, but we also get these forms from holographic calculations, bulk calculations, which Avik will show you. So basically in a quantum system, the out of time order correlator is of the following form. And the Lyapunov exponent here is 2 pi by beta. So in a thermal quantum system, we have derived the Lyapunov exponent to be 2 pi by beta. And we will see a bound on the Lyapunov exponent in the next part for a generic quantum system. So any questions till this point? Okay.
Hello.
Yes.
Can you make me clear about the limits once more? This HSLL and this.
All right. So here, so both HW and HV are kind of small with respect to central charge. But then I was taking HV here to be larger than HW. But now I'm taking HV also to be kind of small. So it's going towards, so basically it was earlier.
Hello, Surbhi just dropped out, is it?
Right, yeah, it seems so.
Surbhi, can you hear us? Like her iPad is still connected. I can see. What to do?
First, pause the meeting.
Yeah.
Pause the record.
But in this HHLL limit, do we have this notion of Lyapunov exponent?
I think Surbhi's iPad is also now catching up with her.
Of exponent in HHLL limit also?
Usually it is, yeah, I mean, you can call this to be the Lyapunov exponent even there.
But it's like the fall-off is different, like the nature of the fall-off.
Yeah, so usually the Lyapunov exponent is defined when the out of time order correlator is written in this way.
Okay.
So I would like to add a comment. So Surbhi is telling that I will be doing an LLL limit, but that is actually not completely true. Because at some point, if I go, okay, I will tell you the details. I'm telling to Surbhi. So when I do the shortwave thing, then actually I'm assuming that two of the operators are heavy. I mean, if I try to view it as a propagation of shortwave background, then actually some clearly if you see in your first formula, there is this HW and the HV is not in the same formula. Once you have done this binomial, then it's like all of them are in the same formula, HV and HW. But there is clearly a difference there. So that is like the HHLL limit, no?
You're asking me?
Yeah, I mean, for example, if you the first formula that you have written in blue, so HW and HV is not in the same formula. One is as a power and the other is sitting in the denominator. But once you have done this exponent, I mean this binomial expansion, then in the second formula that you have written now, you cannot say which one is like heavier, which one is light. So so she's probably asking like, is there a Lyapunov growth in that regime as well? Okay, sorry. Now I understand.
Okay, so just let me move on. If there are no further questions on that part, can I move on to the bound? Okay. So, right. So as I was saying that.
No, we have a question actually on that part as well.
Okay.
So
Okay.
Sudeep, if you want to unmute and question.
Yeah, can you hear me, Surbhi?
Yes.
Yeah, so actually I was wondering so in this calculation, what you showed is that the Lyapunov exponent just comes out to be 2 pi by beta. And so it saturates the chaos bound, right? And
yes.
So I was wondering that is there an intuitive way to understand why it saturates the chaos bound? Because you would expect that the chaos bound is saturated in a CFT which has actually classical Einstein gravity duals, right? So in this calculation, so in this calculation, okay.
The CFT has a classical Einstein gravity dual.
But in your calculation, what I was wondering is that, so in this calculation, did you have to assume anywhere some of the features about the spectrum of a 2D CFT which we need to assume for having classical Einstein gravity duals?
Right. So here I assume that we do not have any charges except for the U1 and the stress tensor. So no higher spin.
Okay, I see. I see.
Can I just add a comment?
Yeah.
One more assumption is that you've got vacuum dominance. Is that not that you're approximating this 4-point function just by V0 only. So you have a sparse spectrum of primary operators, which is needed in order to have a Hawking-Page transition if you are in Einstein gravity. Yeah. And in that regime, you approximate the correlator by a single block, which is the identity block, and therefore you also.
Thanks, Shavik.
Sorry, may I ask one question related to this to solve it actually?
Yeah, Avik, actually, I'm not able to. I'm not able to hear you properly. That's all I'm saying.
Okay, maybe I'll ask you.
Yeah.
I think let's move on then.
Okay. Right. So yeah, as I showed for the thermal so basically there exists a bound on the Lyapunov exponent for thermal quantum systems. And what we showed for the 2D thermal CFT, which admits an Einstein gravity dual, is that we just showed that the Lyapunov exponent is 2 pi by beta. And so basically this particular value is because the setup we considered admits Einstein gravity dual. However, for a generic thermal quantum system, there exists a bound on a rate of growth of chaos. In thermal quantum systems. Finite. With large but finite degrees of freedom. With large but finite numbers of degrees of freedom. So, so basically what that means is that one, the OTOC cannot grow faster than exponential. And two, that the bound on the Lyapunov exponent is 2 pi by beta. And there's also an H cross, but normally we just put that to be 1. So there was also an H cross here, but we put that to be 1. Right. So the proof of this bound, it depends. It's based on certain mathematical theorem. So I'll just give the mathematical theorem. So given a function f of t, which satisfies following. So f of t plus I tau is analytic for t greater than 0 and in half strip. So by half strip, I mean this. So then the function satisfies the following inequality. So we make use of this theorem to prove that there is a bound on the Lyapunov exponent. I mean, you just saw that the OTOC was of the following form. Right. So I'm just denoting by epsilon all the quantities that we got, which were proportional to, 1 over C. So we got a coefficient in the OTOC, which was proportional to 1 over C. And in the large C limit, that becomes a small quantity. So for a function of this form, if we put this function in the inequality I wrote on the previous slide, this inequality will give you lambda L to be less than 2 pi by beta. Now, I still haven't explained why the out of time order correlator should satisfy all these three properties. But all I'm saying is that if it does, and if so, then this property will mean the following bound on the Lyapunov exponent.
I have a question. maybe.
Yeah. You can. This is a good point to like stop for questions. So
So one question is that, like, can you go just to the assumptions about the thing, just to show previous slide?
yeah.
Uh, is there any chance to modify the point number 3 in the sense that if is one some normalization issue, like I can have ft plus I tau less than equal to x, and then I'll say that it satisfy 1 by x minus f del f del t less than equal to 2 pi by beta. Is that somewhat is that?
Yeah, I think the final proof has some relaxation on the point number 3, basically.
Acha,
The-
no, okay. Yeah, okay. What sort of relaxations?
Right. So I think yeah, I will come to it, but they show that so basically the function
Hmm.
the f goes something like a function of time by some normalization,
Mm-hmm.
and then they show that this function
Hmm.
is less than fd plus some epsilon. So is that kind of a thing that you're talking about?
1 second. Okay, maybe you should. Yeah, maybe this is what I had in mind, but yeah, okay. I'll wait till you.
Yeah, this will this we can discuss like at a later point,
Yeah.
maybe. Right. Yeah, questions? Okay. Right. So now to try and show why the thermal out of time order correlator satisfies those 3 criteria of the theorem, let's again recall what the out of time order correlator was. So the thermal out of time order correlator was the following. Where y to the power 4 is this. So instead of working, so what that means, right, so let me write down. So instead of working with this correlator, we work with a regularized correlator. So basically what that means is, so what I've drawn here for the first correlator, I have drawn here, the circle is the imaginary time circle, which has a period of beta. And then this is the real time. So essentially the v is at 0 and this is at non-zero time. But then for this regularized correlator, what we have done is that we have moved these operators the quarter of the circle. So to get the second correlator, we have shifted this v operator by beta by 4 to get the second correlator. And it has been shown that these two are equivalent, and one can talk about this instead of the OTOC, and prove the conditions on this function instead of on the OTOC.
Shubham has a question.
Yeah.
Why was regularization required? Because of near distance singularities or?
Yes.
Okay.
Yeah. Okay. All right. So this is the circle is imaginary time circle. And these protrusions, they are real time evolution. Okay. So what that means is that this function is the following. Okay, so and so f of t plus I tau is okay. So as you can see already that the first point is that for a finite number of degrees of freedom, this function f of t plus I tau is analytic in the tau less than equal to beta by 4 pi strip. And the second point is that at tau equals 0, this function is real. So at this point, if you have any more questions.
Oh, sorry, I didn't understand what, how was point number 1 automatically satisfied?
Okay.
I mean, to say that independent of nature of V and W, how are we making this statement?
Okay, so this is, I mean, this is already, I mean, this is verified by some property of traces. Okay, let me just try to recall that. So this function doesn't have any singularities in this region, basically.
I'm saying that, like, is there any way to see that? Because
Can I make a comment?
yeah.
Uh, I, 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 I think it's some argument along the line. If you put some energy eigenstates or something, all the exponentials are suppressing factors if tau is less than beta by 4.
I see. Okay. I see.
Okay, so basically, and then the third property is something that I'm not going to prove here, but it is more involved. So I will just refer you to the paper for this particular property. Yeah, any questions so far?
I mean, I have one simple question that Akhil probably answered. I didn't understand. I mean, if t plus I tau, when you are saying analytic, you don't need anything, any comment on the structure of V or W?
No, that's not needed actually. Because of I think it just depends on these exponentials here. And that was Akhil's comment.
Okay, probably
It's the
didn't
way
understand.
they grow. It's the way they grow. So
Mhm.
how the exponential grows. For time, it decays for times between minus beta by 4 and plus minus beta by 4.
And perhaps because of the weird ordering, you can't ever have OP singularities appearing. Because like VW, VW, it can't ever be VVW. Can't be V2. The two V's cannot come close to each other. In some sense,
Okay.
right? I mean,
Is that assumption? I mean, how can oh, probably the ordering is
of
fixed
this,
or something.
I mean, you can think of this as like evolution in time, right? They are separated by time. Yeah, like I mean, V
In
and
some
W
sense.
insertion, then V and then W insertion. You can't jump over.
Okay, I mean, what you're saying is probably that if t plus I tau is analytic, if you maintain the ordering as well or something, some other statement.
Maybe, yeah.
Okay, but we can check it anyway. So
Can I just make a comment? Like, I mean, what are the
Sure.
possible singularities? It's just the OP singularities to ruled out because we have separated all these guys around the circle. And then I think it's like the standard QM argument, like talking about, oh, is it analytic above the plane, is it analytic below the plane kind of argument, where you just put some energy eigenstates in between every operator, and then all of them will give you some oscillatory factors with energy, but then all the oscillatory factors are accompanied with the positive suppressing decay factors because beta by 4 is greater than tau. So it's some statement along that line. So you just assume some eigenenergy basis decomposition of this V and W, and you'll see that they can't grow. It's some summation over the V energy 1, V energy 2 components and so on.
Excellent. Okay. By the way, Surbhi, you are already in 45 minutes of your talk. So if you want.
Yeah. So as I had not anticipated such less questions, I am done for whatever I had planned for today.
Oh, okay. Okay. So we can be okay. People can ask questions now. Okay. Excellent. Okay.
Yeah.
Could you comment a bit about all these analytic assumptions about the functions? Like why I didn't very much appreciate what those conditions were doing to the function.
These. So you want to discuss this, or do you want to discuss it for the specific function?
I probably first this.
Okay. Right. So, so I don't know if I can present all the arguments exactly, but it has something to do with with hyperbolic functions and a transformation from one plane to the other. So there is a function like this. It's a function of these f's. Sorry, of the t. And then this it maps one plane to the other, and then f as a function of z has some metric, basically some ds square. I don't remember the exact form. dz power something like that. 1 minus something here, and basically in that particular form, some function of z. So there is a mathematical property of these hyperbolic functions. So then because of that, this is satisfied for this if the function satisfies these three, then this is satisfied. I can write the exact function for you if you want.
What was the property of the the metric, right?
Uh,
It's used for some transformation.
it's like a hyperbolic space is used. Let me just write down the exact function. Right. So then the bar will obviously have a minus sign here. And then this metric is and then what it uses is the property that what it uses is the property that because of this transformation of a function from a unit disk into another unit disk, this function b of f is less than this. And this, if you substitute the z here, then you get the 2 pi by beta.
So in terms of the z variable, if z becomes what, like so in the previous slide it was as a function of t plus I tau, then you employ this this change of variable z is equal to Shine hyperbolic something, and then so now if z is on some disk or something, is it because
Yeah, so
of this
basically, I mean, if you take any function, f of t was of the form 1 minus epsilon e to the power lambda lt, and then you can substitute the inverse transformation
yes,
to get f of z.
okay, so okay.
Can I interrupt? Like, I didn't follow what this metric and
Yeah, like
I didn't understand the nature of the argument. Sorry, could you say it again?
Basically, what it says is that, I mean, it's a mathematical theorem, and it uses the fact that it uses this transformation, this transformation from one unit disk into another unit disk. And then it says that, so basically these functions, they cannot increase distances in the hyperbolic metric, and this is the hyperbolic metric. This function satisfies the hyperbolic metric, and so basically it's a property of such a function which is analytic in the half strip, that it satisfies this. So it's a mathematical theorem. I'm not sure I can do justice to it, but you can refer to the paper.
Nihal, if you want to ask the question directly, you can come forward. So he's saying that he's in a library, so cannot speak. I will just read out what he just sent the message. He said that, sorry, maybe I missed some parts, but the inverse temperature, which is beta, appears in the third inequality, and hence Leopard of exponent. So, okay, third equality beta appears, okay, because of the analyticity condition in the half strip, right? Okay, So is it guaranteed that all ft will be analytic in this range? This range cannot be constrained further. That's the question. So what he is asking is basically, is it guaranteed that all function of t will be analytic in this range? I mean, probably the half strip, and this range cannot be constrained further. Okay.
Yes. Maybe I can read the question again.
Sure, please. That would give you help.
Nihal, was it?
Yes, the last message.
So the inverse temperature beta appears in the first inequality. Yeah, and also in the last inequality. Yes, if this function is analytic in the, so the OTOC is analytic in the entire half strip.
Probably what he is asking that whether ft can be constrained further. I mean, inside that strip also, or something similar.
Oh, but how will that help?
That,
I mean, for the bound, this much is sufficient, is what I want to say.
Can I make a interpret and comment on the question?
Sure,
Yes.
Akhil. Anyway, you will do it, so please.
I don't know, like, okay. But
Go
like,
ahead. Go ahead. You will do it.
so I mean, I guess he's just asking, like, how do you know it's beta by 4 is the maximal thing, right? So you seem to, the general function argument is saying there is some beta by 4 in which the beta by 2 length strip around the real line in which the function is bound. And from that, you immediately seem the last point gives you some 2 pi by beta, and that seems to be the maximal Lyapunov exponent. So he's
Yes.
asking, like, whether, how do I know the correlator isn't like.
So basically, I could have just said that this is some function x minus x.
Right, and x gives you a Lyapunov exponent.
I mean, at the level of just the mathematical theorem, this could have just been some x and x and minus x, and then this would have been.
And pi by 2 x will be the maximal Lyapunov exponent. Correct.
Yeah.
Right.
So I guess he's asking, how do you, like, is it more constrained or something? And I guess the answer, like, immediately gives us some more points, right? Like, the answer is that, like, the way it should be regulated, that function, you had 4 points, 4 operators to insert. Hence, you inserted them at some equidistant beta by 4, beta by 4 arcs, separated by beta by 4 arcs, and then you got this x as beta by 4. So I guess it immediately suggests that, oh, if you had a 6-point OTO, you would probably end up with a beta by 6 separation arc, and the x is correspondingly beta by 6. Yeah, and then that would probably give you the Lyapunov exponent for higher OTOs and so on. I don't remember how the 6-point OTO is bounded, but, like, I guess this probably gives you that answer.
Okay, I'm not sure about the 6-point out of time order correlator.
Yeah, I mean, has anyone looked at it, like 6-point auto? Loga has some papers, right? Loga, or I don't remember.
I'm embarrassed to say I don't know. Okay.
Anyway, we can move on if something is there. Should we want to go on?
Right. No, I can stop for questions, and I can I just wanted to make sure that you guys didn't have any more questions on any of these parts.
Sorry, I have a stupid question regarding the CFT computation. In this thing, where is the beta?
The beta is in the cross ratio. Where did I write the cross? Yeah, in the cross ratio.
Yeah, I had a question. Like, can I ask if
Yeah.
Shubham is done? Yes. So someone was commenting about in this when the operator h omega is not small enough, you can't expand this vacuum block or something, right? Like that, then you can't bring it to the standard form in which you compare Lyapunov exponents. Isn't that also a question of time? Like as you like, even if you want to say I can take small h omega and expand it, you can expand it only up to some particular time, right? Because there's an exponential growth. Or am I confused? Like,
So this HW is the conformal dimension of the W operator.
right, but the factor with it is 1 minus eta, right? Like, does that become big with time? Like, or
Yes, it becomes big with time.
so then after some time you won't be able to expand this. Even if h omega is small, you won't be able to expand the denominator, right? To bring it to that standard form in which you want to compare Lyapunov exponent.
Sorry, 1 minus eta becomes small. So 1 minus eta goes to 1 in the large time limit.
Right. So when h omega is, even if h omega is small, I shouldn't be able to. Is that correct? Like I'm maybe confused that I shouldn't be able to expand the denominator and bring this to the standard Lyapunov exponent form when you cross a particular time. Is that, or is it fine after a particular time? Like I'm confused how the order works.
I'm not able to get your question actually. If somebody else understands the question itself.
Well, when this 1 over 1 minus eta is in the denominator, I think it holds for any time. Okay. But for the binomial expansion, as you were saying, indeed, there is probably a regime where this t is much less than t star. It's not evident in this current notation. I'll probably try to show not tomorrow, day after tomorrow. So there is probably a regime in time where you can actually still do this binomial expansion.
So it's invalidated after a particular time. Is that what you're saying?
After you're binomially expanded, yes, then it has to be less than t scrambling. Because that is the, so when this, so 1 minus e to the power lambda t or lambda t minus t star, at that point, in that expression, t is always much less than t star. But that's after the expansion, right? Before the expansion, when the 1 minus eta is in the numerator, this is holds for any t. Just that beyond t equal to t star, this will start decreasing probably. It's not probably quite clear in this language, but yeah, I'll try to show that. So did I answer you, or is I'm still confused?
Yeah, I think if like this expression is more written out in a like expanded out and like, yeah, like I'm confused. Like, okay, my confusion was kind of like this. Like, am I allowed to do that binomial expansion for all times or not? And if I'm not allowed to do it after a beyond a time, probably that gives me a point where.
No, actually, there is no upper limit. That's what I'm saying. I mean, if you keep it growing, so the idea is that you can do it for certain. I mean, how to place it? Okay. So all I'm saying is that when this 1 minus eta is in the denominator, there is actually, you can actually tune your t and this c, h over c, such that this object is still small. Then you can expand. But for that to hold, your t must be much less than t star. Okay. In some way.
Sorry, I mean the Lyapunov exponent is looked at only after t greater than t star, right?
No, not t greater than. The Lyapunov behavior is for t greater than t diffusion, less than t scrambling. That is the regime of exponential. After t scrambling, it's either saturates or falls or something like that happens.
I thought t scrambling is the time where like the Lyapunov growth really overcomes the large 1 by n suppression and.
Yeah.
I'm probably not for. Okay, I'm confused about what you comment. Okay.
I think if there are no further questions, we can probably end early today because it might be already a very long day.
Sure. So organizers, you can, if anybody has some other questions related to the first part or something, then ask the question, or else organizers can